So we understood the basic machine learning architecture, the paradigm, right? The 3 steps, which is representation, evaluation, finally optimization, right? And we looked at different machine learning paradigms, and we were talking about representation learning or deep neural networks. We saw what was a perceptron, right? How we can extend it to multi-layer perceptrons with nonlinear activations, and we understood how that architecture looks like, right? So you have one layer of nodes connected to another layer of nodes with certain weights, and how each node is processing the input that it receives through a simple linear aggregator followed by an application of a nonlinear activation function, right? That's where we were. And the question that you raised was that suppose these activations, what we saw was this neural network is essentially a function composition. And I want you to remember this, okay? Because this is very important when we talk about training the neural network. This function composition is actually going to help us enormously when you do a training of the network. So one of you asked, suppose those activation functions were linear, right? What would happen? Well, if all the activation functions are linear, you would essentially have a function composition of linear functions. And as you know, a function composition of linear function is equivalent to a single linear function. So it's not going to do anything for us, right? So we are really not interested in linear feed-forward networks. What interests us are nonlinear feed-forward networks, which means we need to define what are the possibilities, or we have to define what possibilities for the nonlinear activation function. Okay, so the first nonlinear activation function, traditionally is the sigmoid activation function. The form for the sigmoid activation function is this S-shaped curve. The way I visualize the sigmoid activation function, if you see the domain is the entire real line, right? And the range is 0, 1. So it just takes any it's taking your real line output and squishing it within the interval 0, 1, right? If you take any real number, it converts into a value within the interval 0, 1. And importantly, as the real number goes closer and closer to positive infinity, sigmoid converges to 1, and on the other direction it converges to 0. Okay, it is a continuous function, it is a differentiable function. Soon you will understand why you need differentiability. Okay, it's a differentiable function, and a very interesting property is the derivative of the function can be expressed as the value of the function itself. So f dash of the sigmoid, the derivative of the sigmoid, is nothing but the function value multiplied by 1 minus f of x. 1 minus the function value. So you actually don't need to have some other complex expression expressing the derivative for this particular function. If you know what is f of x, right, you can directly compute what is the derivative at any point. Okay, again, why is this important? We will come back to that a bit later. All right, great. But there is a problem with this sigmoid function, okay, and that is commonly referred to as a saturation problem. If at any point in your training process, right, the output of the sigmoid, so you're using the sigmoid at some intermediate node in your network, and the output is becoming very large, the output of the aggregator is tending towards positive infinity. So the output of the sigmoid will be closer to 1. What is the derivative of the sigmoid as you go closer to 1? 0. Similarly, as the input is closer to negative infinity, the derivative of sigmoid is 0. So if your optimizer is looking at the derivative to update those weights, if you have a sigmoid which is getting saturated either in the positive direction or in the negative direction, there are no meaningful gradients which flow through the network. So your update becomes challenging. Are you understanding that point? Yeah? Okay. So that is one issue. That is the gradients at the tails tend to 0, which can lead to the saturation problem. And the outputs that you have here, they are not 0 centered. They are centered at 0.5. Right? So the output of sigmoid is always positive. And if you have to use a sigmoid at an intermediate layer, you would like to have a rich representation, which includes both positive and perhaps negative outputs, or at least a 0 output. Even that is not possible with a sigmoid. Okay? But sigmoid was traditionally the first activation function, nonlinear activation function, which was used. Next, you have a Tannage activation function, which is something like an elongated sigmoid, because now it is centered at 0. And the expression for the Tannage function is 2 into sigma to x, where the sigma actually refers to a sigmoid function. Okay? So for large positive inputs, the output of Tannage is 1. And for large negative inputs, the output is -1. And it is centered at 0, which is very good. It is also continuous and differentiable. And the derivative again can be expressed in terms of the input function itself, or the input function value at that point. Okay? Which is good for us. All right. Next, you have the ReLU activation function, which stands for rectified linear unit. So given input x, the ReLU is max of 0 of x. If the input is positive, you just return if the aggregator's output is positive, you just return it as it is. Else, you threshold it at 0 and pass it out. Right? So this is the shape of your ReLU activation function. Right? So if I go back to the Tannage, does Tannage have the saturation problem? Yes, right? As you go towards either highly positive values or highly negative values, the gradient tends to be 0. Whereas if you look at ReLU, at least in the positive quadrant, right? What is the gradient? 1, right? It can never go to 0. So there is some meaningful gradient which will always flow through if you were to find the derivative of the ReLU. Of course, you might ask me, well, this is it a continuous function? It is a differentiable function? At 0, right? It is not differentiable at 0. Well, it is okay. I'm going to assume the derivative at 0 is 0. And I can still go ahead, right? And that's what we do. There is something called subgradients, right? So we can use a subgradient principle here. And basically what we assume is that for an input which is greater than 0, the derivative is 1, else it is 0. And we can still go through with the update process. The advantage is computationally more efficient. All you have to do is a max operator, right? If the value is greater than 0, you output the value, otherwise you output as 0. It doesn't have the saturation problem, at least in the positive side. When the input is positive, you have a constant gradient. And it can have sparse activations, right? So if you imagine you have a layer, a hidden layer, which has say 100 units. And each of these 100 units have ReLU activations, right? Because of how the nature of data processing happens, the feed-forward pass, many of these nodes may not be active because the aggregator's output will be negative. In which case, only a subset of these nodes get activated. And it is this activation which is fed forward to the next layer, right? So it can lead to sparse activations. Okay.
I have a question.
Yeah.
It might be just a silly question, but from the sigmoid function, you went to the tan hyperbolic function because it was not centered around 0. But can't you just translate and scale the function, the sigmoid function, to be centered around 0?
Yeah, you can do that, but you would still like the output to be 0, -1 or 1. You can definitely do that.
So what's the advantage of tan hyperbolic over a scaled and translated sigmoid function then?
Right?
Yeah, in principle, yeah.
No, it is.
Yeah.
It is. That's what I'm saying.
Oh, right. Yeah. Of course. That's why I said it was a silly question.
A disadvantage is, yes, it is non-zero centered. It is unbounded, right? If it is positive, the value is unbounded, and can also lead to something called as dying relus, that is units which are pushed into states from which they can never recover. They always remain dead. So there is no update which happens to the weights connecting to that ReLU network, ReLU unit. Okay, let's not worry about that too much for now. So if you look at our machine learning model paradigm, what have we done so far in the context of neural networks? We have essentially defined our representation, right? Which is in the form of this multi-layer network, right? And the parameters which define this network, right, are what? What are the parameters which define the network? The weights, right? There are other choices as well, which is number of layers, width of a layer, and so on, which in our machine learning community we call as hyperparameters. Okay. For now, we are not very concerned about that. Okay. The parameters that given a network, the parameters that we try to learn are the weights of that network. Clear? So we have defined our representation. Our next goal is to define the evaluation function, right? And we would like this evaluation function to be a function of the weights of the network so that you can optimize it and learn. Right. So now the problem statement is, we have been given a set of trainings, a train set consisting of input-output pairs. There are n such data points. Xi is an input. Yi is a corresponding output. Yi can be continuous, can be discrete, can be ordinal, whatever it is. Okay. And we have parameterized the function f from this input d-dimensional space to the output space y as a neural network. Therefore, the parameters to be learned are the weights of the neural network, the weights at every layer of the neural network. The next step would be to define the evaluation function L in terms of the parameters of this network. Okay. So for that, you may have to understand how we can define Xi, how we define Yi, and therefore what could be the evaluation. So let's look at representing the input. How can we represent your data as input to this network? After all, the network is only seeing numbers. So whatever data you have to convert it into numbers, because it's basically doing basic arithmetic operations, right? So it can be just vector of numbers, or it can be a scalar if your input is just a single value, right? So if it is an image, you have a vector of pixel values, right? So these are basically raw pixel intensities. If you are working with audio data, you might be tempted to extract certain, audio speech features, right? Like say Mel-Substral coefficients, or say you're doing some other wavelet transform and extracting those features. So it could be those features which you're extracting from the input. If you're working with documents, you might be tempted to represent the document as a vector, probably a binary vector, right? Indicating the presence or absence of a set of words from your vocabulary in that document. Or it could be the count of the words occurring in the document, count of the unique words occurring in the document, and so on and so forth, right? So you have some mechanism to express your input, which is typically a vector of numbers. Is that clear? So if you're dealing with your temporal systems, right? you could think the input to be a sequence of a specific length. Just the raw data. That can be given as input to your neural net. Okay? All right. How do you represent the output? And that would depend upon the type of supervised learning you are dealing with. If we are dealing with regression, that means the output is real valued. If the desired output is real valued, you can have a scalar output, in which case it is just a regression with output being just one value, right? So, and the output node does not have any activation, right? That gives you the ability to model the entire real line. If you have to regress to multiple output values, then your output will be a vector. And the dimensionality of that vector is determined by the number of outputs that you need, right? So it will be O1, O2, etc. till OK. And each of these might still be without any activation to give it the full freedom to learn the entire real line for each of the outputs, right? So either a single output or a vector of outputs. Is that clear? So for regression, it is very clear because you're already familiar with it. What about if it is classification? If your desired output is binary, 0, 1, or +1, -1, right? You can either pick the output to be a sigmoid, right? O will have the sigmoid activation, and you interpret the output as the probability of the data point X taking the class label 1 given the data, given X. Probability of Y equals 1 given X. The output of the sigmoid is always between 0 and 1, right? So this is the interpretation that we can give. We have only a single output, even though there are two classes, we have only a single output, and this output is the interpretation that probability of that given data point belonging to the class 1. So what will be the probability of X belonging to the other class? 1 minus this value, right? We don't have to explicitly model that. That's what I was trying to get at, right? And if you use sigmoid as the activation function for this output node, it is also differentiable. Yes? It is clear? Okay. If you have, on the other hand, multi-classification, that is, there can be multiple classes. So if you look at an image classification example, the output can be, say, dog, cat, cow, or horse. Of course, they don't have any order that is defined on them, right? They are just symbols from the network's perspective. So how do we convert these symbols into some representation, a vector representation, which the network can then use for the training process? The most common way to do that is through this one-hot encoding vector, where for each class, so you have this 4-dimensional vector, okay? And for an input which belongs to the dog class, the first index is 1, the rest all are zeros. If it belongs to the cat class, the second index is 1, the rest all are zeros, and so on and so forth. So basically, we are using unit vectors of 4 dimensions to represent these 4 classes, right? And here too, you can actually give that probabilistic interpretation, right? The probability of the data point belonging to the cat class is 1, the rest all probabilities are zeros. Yes? Same thing with, say, the horse class. If the 4th index is 1, then the probability that the data point belongs to the horse class is 1, the rest all are zeros. Okay? So for any input class, we will have this 4-dimensional vector output with 3 zeros and a single 1 at the position of that class. And this is referred to as the one-hot vector representation or the one-hot encoding. Okay? So you would like the output of the network to be as close as possible to one of these vectors, right? Yes? Okay. Right. So in general, if you have k classes, so for a multi-class classifier with k classes, one hot representation will have k binary outputs. So the output layer will have k nodes, right? And ideally, we would like the output to be a value between 0 and 1. And what should be the other property to have the probabilistic interpretation? It should sum up to 1. How do we achieve it? We'll see that. So the neural network's output must ideally be binary. From where is that? Yeah.
So why do you, if they're all probabilistic, then you don't need one of the dimensions at all, right? You can get by
Yes.
k minus 1.
So if k minus 1.
Yeah.
That's what I have written here. Ideally, you need k minus 1 dimensions, but to make it easier, we have just k. That's all. You're right. Can you remove that arrow from the middle? I'm not able to do it from here. Okay. Yeah. Input can be anything. It can be images, it can be documents, it can be your time series, it can be anything. Just that the output is associated with a label, which is a class label. It doesn't have any order defined on those labels. Got it? Okay. So if there are k outputs, ideally, as you were saying, you can just it's sufficient to have k minus 1. But for completeness sake, we'll just go with k. We ideally want k minus 1 places to have zeros and one place to have 1, or all should sum up to 1, right? So more realistically, it will be a probability vector of k dimensions, and the k probability values sum up to 1. How do we achieve it? We use the softmax vector activation. And this is one trick you will see again and again in machine learning literature. When you want to have an output which is of say k dimensions, and you want to treat it as a probabilistic interpretation, all you have to do is apply this softmax activation. What is it essentially doing is the following. ZKL is the output of the linear aggregator at the node k. Okay? ZKL is the linear aggregator's output. You look at all the linear aggregator outputs at the output node. Exponent of one of those divided by the sum will give you that probability. Okay? Yeah? All right. So this particular operation, which is a softmax vector activation, is what is used to convert this representation to a probabilistic vector. A vector between 0 and 1, the values between 0 and 1 and summing up to 1. Is that clear? Yes. And this can be viewed as the probability y hat k, indicating it is the predicted probability of the data point x belonging to class K. And this is for one particular output node. If you do this across all output nodes, you will end up with what will you end up with? A distribution over the number of classes. Right? So if you were to, it looks like that slide got deleted. So this is the output for one particular class. If you were to repeat this for all the output nodes, which is for all the classes, you will get a probability distribution over the possible outputs. And what would be your goal? To match this distribution to the ground truth distribution, which is your one hot encoding. Yeah? Great. So now we have understood how to represent our inputs how to represent our outputs, right? So what is the network giving as output? Our next goal is to define the evaluation function. So given a training set of input-output pairs, we perform a forward pass or the feed-forward pass of the network. So you take the input, pass it through the network, performing the linear aggregations and the nonlinear activations, one layer after the other. Eventually, you will get to the output layers, linear aggregation, followed by the activation which is defined on the output layer, right? And you will have the output of the network, which is the predicted output of the network, which is y hat I for each of those n data points. Now we need to define an evaluation function, L of capital W, where this capital W refers to the parameters of your neural network, the weights of your neural network, right? How do we define this? If it is a regression task, you can just do the L2 divergence or the L2 norm, all right, between the two outputs, right? So when will you use this? You can use this even for classification. You can also use this for regression, but more often this is used for regression, right? So you have your predicted output y hat. Y is the actual output. You're just computing the distance between those two vectors. That's all it is. Nothing too complicated, right? And if I do this, if I define my loss function in this way, I can also find the derivative of this loss function with respect to the predicted output y hat. What is the derivative of this expression with respect to y hat? It is basically this vector that you see there. That is clear, right? Yes? So you know the derivative with respect to a scalar. This is derivative with respect to a vector. And that vector here is nothing but y hat. Okay? So I am able to express the derivative of the loss function with respect to the output of the network. You may ask, why is this important? We will see it very soon. What are we interested in? We are interested in updating W, the parameters of the network. Okay, keep that in mind. All right. So if if I take the L2 divergence, I have the derivative of the loss with respect to my output y. If it is a classification task, we typically use the cross entropy error. Okay, you might have actually come across this in a different form, the Kale divergence, right? So we can derive this from the Kale divergence itself. So for a binary classifier, the actual output is 0 or 1, which can be interpreted as a true probability distribution y comma 1 minus y, right? So the predicted probability is y hat, which is the probability of the data point belonging to one particular class, and the probability for the other class is just 1 minus y hat. So we have one ground truth distribution, which is this. The other distribution is this. So what do you have to compute now? Divergence between these two distributions. Right? Right? And are you familiar with the Kale divergence expression? Kale between P and Q? Can anyone help us out? Let's assume that they are discrete distributions. Can you help us out, please? Kale between P and Q? Summation? P by Q, right? It's P log P by Q minus P log P by Q, right? So if you were to expand that, P is the true distribution, Q is this predicted distribution. If you were to just expand it, you will end up with this particular expression. Okay, there is one more term which really doesn't matter because it is independent of y hat. We are only interested in that part of that loss contributed by y hat, because y hat is what is predicted by the network, right? And when does the minimum occur for this particular expression? When y is equal to y hat. And what is the derivative of this expression with respect to y hat? Is it a very complex expression? Simple. This is minus 1 by y hat if y is equal to 1, and it is 1 by 1 minus y hat if y is equal to 0. Again, you can easily compute the derivative if you know what is the predicted value y hat. Yes? So far things are clear? Any confusions, any questions? Yes. You can do the symmetric KL, right? KL between P and Q plus KL between Q and P, or you can do the Jensen-Shannon divergence, right? Right? Yeah. All right. Okay. Suppose you have multi-class classification setting. That is, there are multiple outputs, multiple classes. So the desired output is this one hot encoding, where in one index you have 1 and the rest of the indices, the values are zeros, right? The output will be what? It will be a probability distribution vector y hat. It will sum up to 1 and the values are between 0 and 1. So now you have to find the divergence between this distribution and this distribution, which is your ground truth. Again, if you compute KL divergence between these two, we will end up with this loss function. Minus k yk log y hat k. The other term will have yk log yk, right? P by q, right? In which case, it really doesn't matter to us because it doesn't have the output of the network. We need y hat to be part of that loss function. So we just need to have this. And this turns out to be just minus log y hat k. Why is that so? Yeah, yk is 1 only at the index k. Rest all entries, it is zeros. So it just boils down to minus log y hat k for the kth node. Yes? Okay. And what is this derivative? This turns out to be minus 1 by 1 y hat k for the kth component, and for the rest of the components it is 0. So the derivative of the loss function with respect to y hat, the true the predicted output, is minus 1 by y hat k at the kth location, because yk is equal to 1 and the rest of the locations it is 0. Yes? Yeah? Okay. Good. So far, we have determined the representation, which is your neural network. We have defined the evaluation function for both, say, a regression task and for classification task. Our next goal is to optimize. What does it mean to say optimize? Given the evaluation and characterization, find the optimum representation. When does one achieve optimum representation? When the loss is minimum, right? So if you have a function f, you want to find the minimum of the function, basic calculus, what do? Yeah. So what do? You find the derivative. Yeah. So how do you find the minimum? You find the derivative. But the derivative doesn't give you the minima. But the derivative gives you, what does it give you? It gives you directly the optima? Yeah. But what direction does the derivative give? It gives you the direction of maximum change. It gives you the direction where the function is actually increasing. But what do you have to do? You are trying to find the minima of the function. So you have to traverse in the opposite direction, right? So that's why we perform gradient descent. Okay. Unfortunately, the loss function for neural networks is not a convex function. Convex in terms of the parameters of the network. Why is that so? Well, we have many nonlinear activation functions in the layers, and that renders it non-convex, right? So you're familiar with optimization, right? I'm assuming, I'm making that big assumption. No. Okay. All right. All right. I made that assumption. Sorry for that. Yeah. So we have this loss surface to be non-convex. Why I stress that is, if your loss surface is convex, and if you were to apply gradient descent, I mean, this is something that you should know. You should already be familiar in your 12th class calculus. There is something called as global optima and a local optima, right? For a convex function, your only optima that you can ever get is a global optima. But if it is not a convex function, it is possible for you to get stuck at a local optima. Okay? And since neural network loss function is not a convex function, when we try gradient descent, you can actually get stuck at a local optima. I'll come to that in a bit. So how do we perform gradient descent? So what does that mean? It means, given a training set, we have to find WJHL, which minimizes this. Okay, so if I have to draw how this gradient descent is working, I'll just draw for a simple one-dimensional function. So this is x, this is f of x, and let's say this is your function f. Okay, so the way this gradient descent technique, if you're not familiar with it, the way it works is, you randomly start at some point, let's call it x0. Okay, so at x0, this is where your function value is. If you find the derivative of f at x0, it would point out something. I'm poor at drawing, so this is the direction of your gradient. And you would like to traverse in the opposite direction. What this gradient descent method tells you is, let's traverse in the opposite direction, but make a small step in that direction. So along x0, we are going in this direction, and we are picking x1. Okay, and that step size is determined by the learning rate of gradient descent eta. Okay, the greater the value of eta, the bigger step size that you make. The smaller the value, the smaller step size that you make. And what is its impact on the convergence of the algorithm? If eta is very large, from here you may do a wild swing and go to the other side. And then again from there you may do a wild swing and come to this side. So there is a high chance of oscillations to eventually converge to the optima. If eta is very small, what would happen? You're making abysmally small steps. It might take ever for you to actually reach the optima, even though you're going in the correct direction. Yes? Yeah? So this is basically gradient descent. And that expression is x new is equal to x old minus eta times the gradient of the function at x old. Okay, this is gradient descent. And this is what is applied for training any neural network. Rather, this is, I would say, I have to carefully state that the fundamental algorithm is gradient descent. You might see some variations where you can have a momentum term, or you can have an adaptive learning rates, and so on. But the basic principle is gradient descent. Is that clear? Yes? So this is basically a way to find the optima of the function. Yeah. Correct. Huh. So, yeah. So the chances of encountering a flat surface in neural network training is remote. What you would expect is a surface which is more like this, riddled with local optimas. And it so happens that it is okay if you converge to any of those local optimas because it gives you decent results. So it's densely populated with good solutions, the loss surface. Okay, but we somehow have to get to one such solution, and a method to go about doing it is gradient descent. Is that clear? Right? I mean, I made this assumption, sorry, otherwise I would have added a couple of slides on, basic gradient descent based optimization. So what is key here? What should we compute to do this optimization? The derivative. And that's why so far in all the slides I've been talking about, oh, it is differentiable, I can find the derivative and I write it in this particular form. Because eventually when I have to train the network, I have to go back and rely on that gradient. Yeah? Okay. But things are still not that simple. Right? What is it that we have to compute? As you said, it is, we have to minimize the loss function with respect to this parameter. That means we have to compute the derivative of the loss function with respect to each of those parameters of the network. Now imagine the situation. This is my input layer. I have layer 1, hidden layer 1, which has a set of nodes and connections. I have H2, another set of nodes and connections. And let's say I have HL hidden layers with corresponding connections. And finally, I have my output layer. Right? We actually have to compute the gradient of the loss, which is computed here with respect to even the weights connecting the input layer to the first hidden layer as well. Right? Can you think of, how complex that looks like? What is this output? Is basically, how did we say we can envision or visualize this neural network? It is a function composition. This y hat is function composition and the first layer weights, right, are somewhere here. And you have to find the derivative of this complex composition with respect to that set of parameters. Now, do you see how challenging it is? Yes, but that can be done very easily. Why is that so? The key to that answer is it is a function composition. Chain rule of differentiation, that comes to our risk. Right? And that is why neural networks are so successful, because the training algorithm relies on computing just a derivative, the applying just the chain rule of differentiation. So if I have to compute, to actually take a much more concrete example, if I have to compute the derivative of a weight which is in the first layer, right? So let's say this is the weight I'm trying to compute. This is one input. This is one hidden layer. This is another layer. And I have my output. Okay. So this is Z1. This is Z2. This is O. And given the output, we know what is the loss function given the true output Y. Okay. So if I know the derivative of L with respect to Z1, right, or the derivative of L with respect to Z1, right, it's easy for me to compute the derivative of L with respect to W. Do you see that? Or let me make things slightly easier. If I know the derivative with respect to Z2, okay, what will be the derivative of L with respect to Z1? Yeah, go ahead. This multiplied by dz1 by dz2 by dz1, right? And this is what we do in our training process, which is the backward pass, which results in the back propagation algorithm. So you start from the output layer, compute the derivative. Remember when we talked about evaluation functions, I also gave you expressions for the derivative of that loss with respect to the outputs of the network, right? Yes. So now if I have to compute the derivative of the weights connecting to the output, all I have to do is find the derivative of the loss with respect to the neural network's output multiplied by the derivative of the output with respect to those weights. So if at any point in time I have computed the derivative of the loss with respect to a certain hidden layer representation, I can in one step compute the derivative for the weights at that particular layer. Do you see that? Yes? Everybody is clear about it? And that is what is the basic backpropagation algorithm. Okay? So how do you compute this? That is through the backpropagation algorithm. So I'm not going to this detailed derivation. I'll just give you a glimpse of it. And the key principle that is being applied is the chain rule of differentiation. Okay? So the point is you don't even have to compute explicit expressions of the derivative and store it somewhere. You can do it in the backward pass. The moment you compute the derivative of a particular layer, you can immediately compute the derivative of the weights connecting to that layer by just doing a simple multiplication. Okay? So you initialize the gradient with respect to the network output, and for all the layers, now here we are going from L minus 1 to 0. A forward pass is from layer 0 to layer L. When we do the backward pass for updating the weights of the network, you go from the outermost layer to the innermost layer, right? So dou L by dou YL, this is an explicit expression. I won't go about deriving this expression, which uses the basic principles of chain rule of differentiation, right? So there are two things which it uses. One is this, and now let's say suppose I have another architecture where I have this, let's say some ZH, and this is contributing or is connected to O1, O2, and O3, right? So you will have a derivative here. What will be this derivative? Or, right? Similarly, I'll have, and here I'll have dl by. What is dl by dzh? You will have to look at the derivative flowing in this direction. You have to look at the derivative flowing in this direction. You have to look at the derivative flowing in this direction. And the derivative here would be the cumulative aggregation from each of these directions. So what will that be? Some rule. Yes, and that is the cumulative gradient which gets accumulated at that. And this is something very common, right? Because one node is connected to all the nodes. So far, the architecture that we have considered, one node is connected to all the nodes in the subsequent layer. So the gradient is going to flow from each of those connections, gets accumulated, which gives you the overall derivative at that particular node. And now this gets distributed to the connections which are coming from here. Is that clear? Yes? Okay. So this is your back propagation algorithm, which is used to train a neural network. And this also uses a principle called automatic differentiation. So if you have heard of these packages, right? TensorFlow, PyTorch, etc., they are very good at implementing this automatic differentiation. And in particular for backward pass, we use the backward differentiation. So what you will notice is when you compute these derivatives, right? When you compute these derivatives, right? They actually turn out to be quantities which you had already estimated in the feed forward pass, in the forward pass. So as long as you store those forward pass values at these nodes, you can very quickly compute the derivatives and do the backward pass. Okay? All right. That's the gist of the backpropagation algorithm, which is used to train a neural network. You really don't have to worry about any of this because it's very efficiently implemented in many of the standard toolboxes that you use. But as I said, your loss surface looks something like this. It is riddled with local optima. So how do you ensure that you get good convergence? So gradient descent can be slow to converge. That is, the successive weight updates can either lead to large oscillations or it can be extremely small updates, taking an enormous time to converge. So one way to improve the convergence is through adding this momentum term, which the concept is very simple, right? If you're rolling a marble on the floor, right, and if there is a small pit, there is a high possibility for the marble to actually cross that pit and go if the momentum initially that is given to it is high, right? That is the same idea here as well. So the optimizer can escape some of these bad local optimas if the momentum that is given for it to traverse is high. And how do we define the momentum? The momentum is defined in terms of the weight updates that it has seen in the past. If I'm going repeatedly in the same direction, then perhaps the momentum along that direction can be high. And that is the basic principle here. So you can use momentum, that's one opportunity, that is one way of improving convergence. Typically, the learning rate is chosen in the interval 0, 0.3. It's a very, very small learning rate that you choose. If you choose too low a learning rate, it can not lead to oscillations, but convergence is slow. If it is too high, then it can lead to oscillations. One way to overcome it is through adaptive learning rate. That is, you check at every iteration whether the loss function is increasing or decreasing. If it is increasing, you may want to give it an additive factor. You increase it by a constant factor, which is in this case A. If the error actually increases, in which case you reduce it, because it appears that you have overshot and gone to the other end, right? So you have this negative multiplicative factor to reduce the learning rate. So increase eta if error decreases, decrease eta if error increases. Typically, you can also follow a learning rate schedule, which is simulated annealing, right? So you initially start with a large learning rate. So what does large learning rate mean visually? What can you think about it as? Large steps. And there are steps in initially you're picking a arbitrary random vector, W, right? So what kind of movement is that? Random movements, right? But as you start approaching an optima, you reduce your learning rate, which results in an annealing process. So initially you allow for random movements, random jumps, But as the convergence, as the iterations proceed, you reduce the possibility of such random jumps. Right? So that is in terms of annealing. The initial weight value. So we had this discussion in the morning's lecture also, right? So what if all the weight vectors are the same? Weight values are the same. The network will not learn anything. So you have to break such symmetries, right? So you start with random values which are close to 0. If the weights are too high, then again there is a problem. Convergence becomes an issue. So initial values cannot be exactly 0, in which case the network will not learn anything. Typically, you pick the weights from a normal distribution in 0 and 1 by root d, where d is the number of dimensions, the dimensions of your input data. Okay. There are other methods also to pick weights. So one interesting method is you look at the interval -1 to 1. Okay. If you have, say, 100 parameters, you split the values from -1 to 1 in increments of 0.01. And each weight takes a unique value. So that is one way of doing it. Then you can do mini batch gradient descent. Okay, so we discussed this gradient descent, right? And this update is with respect to one input point, right? If I have to consider all the inputs, then it becomes a full gradient descent, in which case you're considering a forward pass of all the inputs, computing the loss on every input, and then doing the back propagation part. The challenge with that is if you have millions of data points, you spend so much time just doing the forward pass, right? But the advantage with that is the gradients that you get, right? By considering multiple points, somehow it is getting average. So you get good directions to proceed. But on the other hand, if you consider a single point at a time, what is the problem? It can be quite erratic, right? So for one data point, it might be pointing in one direction. For the next data point, it might be in the opposite direction, right? So some of those gradient updates become cancelled, meaningless. You're spending more time. So a compromise between both is mini batch gradient descent. That is, instead of considering all the points, you consider a batch of points at a time for performing gradient descent to update the network. But this can lead to another problem, which is covariate shift. So ideally, you would expect that the mini batch that you consider should actually characterize your true data. But if you're considering 16 samples, say from 1 million samples, it's not necessary that they will characterize the true data distribution, right? So there might be variations from one batch to another batch, right? And that leads to a problem called covariate shift. How do you address covariate shift? Through batch normalization. That is, you normalize your batch, that is the features, the outputs of a single batch, you normalize it at every layer, but you also enable a mechanism by which this, when you do normalization, basically you are doing, in this context, you are demeaning the data, that is making the mean 0 and variance 1. Okay. But you also allow the flexibility for the model to actually translate it to another location with a different variance. And you learn those parameters. And that is what is batch normalization. It actually helps to overcome this problem of covariate shift. You can also do regularization. So regularization basically means adding this extra term or constraint on the weights of the network. If the weights are allowed to be unconstrained, they can take any arbitrarily large values, right? There is a high chance for the network to actually overfit or memorize your data by picking very large weight values. You prevent it by taking this norm and adding it to your objective function or the loss function. You're trying to minimize this loss, right? So if you're trying to minimize the norm of the weights, basically what are you trying to do? You want the magnitude of the weights to be as small as possible. And that prevents from overfitting. So this is an L2 regularization. If you use the L1 norm, it becomes L1 regularization. So typically we use L2 regularization. You can have max norm constraints, which is if the weight value exceeds a specific threshold, you just cut it at that point. You don't allow it to increase beyond a specific value. You can also do that with the gradient, which is called gradient clipping, right? And another solution for avoiding overfitting is dropout, where during training time, you randomly drop some of the nodes from the network, with some probability P. So it basically refers to training an ensemble of neural networks. And the difference between one network and another network in this ensemble is the nodes which are active during the training process. In that way, you can also reduce overfitting. Okay, I'll stop here. Is it time? I'll stop here right at this point. Next, we will see, very basic convolutional neural networks and some very short discussion on recurrent neural networks. Okay? All right. So we looked at the basic feed-forward network, right? So if we look at the current spectrum of deep neural networks, right? They all follow the same principles. You might see some differences in the architecture, probably the choice of activation functions or the loss of activation function, loss functions and so on. But the overall process is the same, and the training algorithm which is applied to learn the network is still the backpropagation algorithm. Okay? All right. One variant of a feed-forward network, which is very popular for handling grid-type data sets, an example of which is an image. An image is a 2D grid. And it's actually a 3D grid, right? So image is the RGB channels, red, green, and blue channels, and each channel is basically a matrix, right? So one neural network, one variant of a feed-forward network, which is very popular at handling such grid-type data is convolutional neural network. So we will spend some time understanding how a convolutional neural network works, what is the convolution operation, and other things associated with CNNs. So this is how a general architecture for a convolutional neural network will look like. You have an input image. On this input image, we perform a set of convolution operations resulting in certain outputs, which are then downsampled. Downsample means you're reducing the size. So initially, say it was n cross n matrix. We reduce it to now an n by 2 cross n by 2 matrix, and so on and so forth, right? So we perform a downsampling operation. And onto this, again, we perform a convolution operation, then do downsampling, and keep on repeating this multiple times. Eventually, we end up with this representation, which is basically some encoding of, the feature maps of the input image, which are then flattened and fed to your feed-forward network. So from here onwards, right, so the multi-layer perceptron that you see here, this is basically your feed-forward network. But the input to this feed-forward network is obtained through a series of convolution operations and downsampling operations. And our goal, in today's lecture is to actually understand what happens in this part of the CNN, because you've already seen what happens here in the previous lecture. Okay? So what is a convolution layer? So we are looking at some intermediate convolution layer, and the output of the convolution layer is typically referred to as maps. It's either an activation map or a feature map. Okay? And let's assume that here you have the activation maps from the previous layer. So from the previous convolution layer, We perform the convolution operation and the downsampling operation, whatever it is, and we ended up with a set of feature maps or the activation maps. And onto these feature maps, we perform a new convolution operation. Okay? And if you notice, this feature map is connected to the feature maps coming out of the next convolution operation, all the feature maps. Yes? Okay? All right. And each activation map has actually two components, which we have already seen in the past. One is the linear aggregation, followed by a nonlinear activation. So you have a linear map which is obtained by the convolution operation. Previously, it was a simple linear aggregation, right? Summation I wi xi is what we were doing earlier. But that now gets replaced by the convolution operation. It is still a linear operation. Okay? And we perform an activation on top of it. Akin to the weights W, which we saw earlier, here too, we have to learn a set of parameters. And those parameters are the filters which are associated with this convolution operation. Okay? So we perform the convolution operation followed by the activation, and all the maps in the previous layer contribute to each convolution in the next layer. So what is the convolution operation? Are you familiar with convolution? Just show of hands if anybody is familiar with convolution. Okay. So let's take an example to understand this convolution operation. So I have this input here, which is a 5x5 image containing binary pixel intensities, 0 or 1. And this is an example 3x3 convolution filter. Okay? So what we basically do is place the convolution filter on the first 3x3 grid, right? So we multiply, so 1 into 1 plus 0 into 1 plus 1 into 1 plus 0 into 0 and so on. Through these 9 elements, you will end up with the value 4. Then you shift it by, why is this not giving me the, okay, for some reason it's not coming. Okay, so then we shift this by 1 position. Now it is aligned along this 3x3 grid. You will get the second value. Then you put it along these locations, this 3x3 grid, you will get the last value. You go 1 row below, you look at this grid, you will get the first entry in the second row, and so on and so forth. Is that clear? So you're essentially placing the convolution filter on the location on the grid, just multiplying the weights of the convolution filter with the values at those grid locations, summing it up, and that results the output value for convolve feature. Okay? Yeah. What is this filter? Well, that is the set of weights that we will learn through training of the CF. Previously, we had just W's, right? We were just doing WIXI, right? And we wanted to estimate what the values of W are. Here, in addition to those W's, which occur much later in the network, we also want to estimate what should be this filter. What should be the values of this filter? Got it? Yeah? But there is very interesting thing that is happening here. And what is that? This filter weights doesn't change at every location. We apply the same set of weights across the different locations on the input to get one convolved feature map. And that is what is referred to as shared weights. Right? Because the weights, the filter weights, filter is just a 3x3 filter. Right? Just 9 weights you have to learn. And these 9 weights are applied on different locations of the input to get your convolved output. So we perform a scanning operation of the image with this filter. So we put it in the first location, then shifted by 1, then shifted by 1 and finish that entire row. Then you go 1 row below, again do the scanning operations, again go 1 row below, come do the scanning operations. So what would be the size of the convolved feature map? If say there is a K cross K filter and an N cross N feature map, input map, what would be the size of the convolved feature map? K cross K filter, N cross N input. N minus K plus 1 times same, right? It's an N cross N feature map, K cross K filter. Okay. So that will be the size of your convolved feature map, right? So at each location, the filter and the underlying values are multiplied component wise, and the products are added along with this bias term to get the value of the convolved feature map. We don't necessarily have to shift this by 1 location every time. Okay, you can shift it by 2 locations or 3 locations and so on. And what would be the consequence of that? So if I were to shift it by 1 location, I got this feature map. Now if I were to shift it by 2 locations, what would happen? Where do you see a change? In the size of the output, right? The convolved feature map size actually reduces, right? So if you were to pick a different shift, which is what is referred to as the stride parameter, okay? So how much stride does the convolution filter have? If it is more than 1, then in this particular example, if the stride is 2, so first we put at this location, we got the output as 4, then we shifted 2 locations instead of 1, we get the second value. Again, we shifted 2 rows below, then we get the third value and finally the fourth value, right? So if you apply the stride operation, then the size of the convolved feature map also correspondingly reduces. Okay. So this is basically, example with a hop of 2 pixels per shift. And why do you think this is okay? Why do you think we can do this hop instead of doing, 1 row at a time or 1 column at a time? Similar, exactly, right? So you're not expecting to see a significant change between adjacent pixels because the values are almost the same. So you can afford to do these kind of operations. And what is the advantage of doing this? You are able to shrink, you're able to reduce the size of the output, right? Because your input image can be, say, 200 cross 200. If you continue to maintain that same size, right? So the feature map which you eventually feed to a multi-layer feed-forward network would be very large, not able to handle computationally because of limitation in computational resources, right? So in which case, this kind of an operation helps it to make it manageable. So you can also view it in a different view. So here we were looking at a single feature map and a single feature. Now let's assume that you have a set of stacked feature maps from the previous layer. In the input layer, there are 3 feature maps, so to say. What are those? Red, green, and blue channels of the input image. Okay. If there are K filters, right, or L filters at a particular convolution layer, you will have L feature maps, 1 feature map corresponding to each of these filters, right? So if you have a stacked arrangement of these feature maps, your filter is also now a 3D filter, right? I mean, in the sense, we are applying this this filter across all these feature maps to get one particular output. Do you understand that? So how does that work? So you look at the filter which is placed at this location, and you're performing the convolution operation across all these feature maps. So this is your expression for the convolution operation, right? So the term that you see here, K and L, right? They represent this region inside. Okay, inside that rectangle. Now, if I look at, yeah, right? So if I look at this K to L, that represents one map. Now, if I look at all the feature maps which are present, then I have this extra additional summation, which is P. Okay, but if you look at this, your W is S, P, K, L. What does that mean? KL refers to the spatial size of your filter, right? K and L index into the number of rows and columns which are present in your filter. P will index into the feature maps on which the filter is placed, right? S will refer to the filter that you're considering at that location. There can be multiple filters, right? So the Sth filter is what we are looking at. So this is one feature map. And if you look at all, then you have to do this extra summation over P. So it's basically a 3D convolution operation that we are performing. Okay? And the parameters that we have to estimate are this weights at S, P, K, and L locations. Rather, at P, K, L locations, and there are a set of such filters that we have to learn. And W is the filter. W is the filter, Y is your feature map. Right? Yeah. Okay. So this corresponds to the output for the Sth filter at the location I, J. Now what do? You shift it a bit, you will get the next output. You will shift it a bit, you will get the next output, and so on. You keep doing this shifting operation over all the locations. Eventually, you will fill up the convolution feature map for the next layer. Okay? So the computation of the convolutive feature map at any location sums the convolutive outputs at all the planes. The planes here refer to the feature maps coming from the previous layer. Yeah? Okay? So this is what we are doing. And this is your basic convolution operation. So the parameters that you have to consider are the convolution size, right? So if it's an n cross n image, the filter is m cross m, the stride is ms, the output of each filter will be of this particular size, and we are assuming here that we are not allowed to go beyond the edge of the input. If we have to retain the size of the input, we do something referred to as padding. Okay, so we can do a zero padding. We can increase the input size by adding additional rows and columns containing zeros, so that if you were to perform a convolution operation on this padded input, it will result in an output which is the same size as the original input. Yeah? Okay. So that is what it is, and this results in the reduction in the output size. So to overcome that, we do padding. So pad the input image or map all around, pad as symmetrically as possible. For stride 1, the result of this convolution is the same size as that of the original image or the original feature map. So the convolution operation, we have seen the convolution operation now, right? So it's basically a spatial grid of filter which is scanned across all the locations of your input feature map, element-wise multiplication with summation, resulting in your convolution feature map. The next step is apply the activation function, right? So the activation is applied to every entry in this feature map, just like we applied activation in your feed-forward network, where you did the linear aggregation followed by an activation. Instead of linear aggregation, here we have the convolution-based aggregation, and onto that we apply your we apply the activation function. Okay. Another trick which is used for reducing the size, right, as you proceed with multiple convolution operations is pooling. And the idea behind pooling is, especially max pooling is the following, right? Let's say the task is given an input image. I want to know if a car is present in that image. Okay. I want to just classify whether that image contains a car. I am not very concerned about where the car is present in the image. In one image, the car might be present in the top left corner. In another image, it might be present in the bottom right. In another image, it might be in the top right. In another image, can be in the center. But for all of these images, I want the output to be, yes, there is a car. Right? So what matters is the presence of a car more than where it is present in the image. So the max pooling operation actually helps in that sense. So if you have a feature map, you look at small regions of this feature map and only output the maximum value which is present in that region. Okay? So if I have a 4x4 feature map, and if I apply a pooling or a max pooling of stride 2, that means I'm looking at 2x2 grids, and within these 2x2 grids, I'm finding the maximum value and passing it. So do you see when I said, we really are not concerned about where the object is present as long as you're able to tell me that an object is present. So I'm not worried about where is this 6 present. 6 is actually coming from this location. But I want to know that 6 is present. Right? And that is the idea behind max pooling. And one way it helps is to reduce the size of the feature maps, which are then passed to your fully connected networks. So an n cross n image or n cross n picture is compressed by a p cross p pooling filter, with stride D results in an output. I'm not going to this particular details. You can look at it. But the idea behind max pooling is we are interested in, what is the maximum value present, not really where it is present. But you need to keep track of where it is present. For what? So you have the convolution operation followed by the activation, and then we are doing max pooling. Okay? That's the forward pass. Okay? Why do I need to know where is that maximum value is coming from? For the backward pass. Right? The gradient has to flow through. So when you do a max pool, if you have accumulated a certain gradient at this location, that gradient will pass through this location, and the gradients at all the other locations will be 0. Is that clear? Yeah? Okay, good. So the parameters to choose, the design choices when you have a convolutional network are the number of convolution and downsampling layers, right? And the arrangement, what order, the typical order that you follow is convolution with stride followed by max pool and so on. For each convolution layer, the number of filters, the spatial extent of the filter, and the stride parameter. For each downsampling or pooling layer, the spatial extent of that pooling filter, as well as the stride of the pooling filter. And finally, you have that multi-layer perceptron, right, to which you are passing the flattened convolution feature map. So for it, the number of layers and the number of nodes in each layer. This all put together gives you your convolutional neural network. How do you learn a CNN? I'm giving a very high-level bird's eye picture of a CNN. How do you learn a CNN? The training is as the case of a regular ML, right? All you have to do is compute the gradients. But there is something very interesting happening here, right? The gradient with respect to one weight in the convolution filter. So if I go back, if I go back to this, okay? Let's say I have accumulated some gradient in this location, which is 1 cross 2 location. Which all locations in the input does it contribute to? This will correspond to the first location. This is going to also contribute to. Do you understand what I'm asking? Yes? Which all locations in the input feature map, right, does this gradient flow to? To this. So if I look at this particular location 4, which I have numbered as 4, this is going to contribute to each of these 9 locations, right? So if I look at one location in the input feature map, you see the gradients are coming from multiple locations in the subsequent layer. Is that clear? Yes? So that is something that you have to keep in mind when you are doing a convolution operation, convolution neural networks. Okay. Yeah. So the only difference is the structure of the network. Ideally, I mean, not ideally. Theoretically, the operation that is performed by a convolution filter, right? So let's say you have an n cross n input. You performed a convolution with filter of size k. Let's say you did 0 padding, you still get an n cross n output. This can also be performed by a fully connected network, which means every input node is connected to every output node. But the number of parameters which is required for such a fully connected network would be n square, right? Whereas you're able to perform the same operation using shared features using just k cross k filters, k cross k filter weights. So the shared weights actually reduces the number of parameters that have to be learned for performing the same operation. Okay? All right. So the training examples would have the image and class, as we have seen before. We define a loss between the desired and true output of the network in response to any input, which is already that we have seen before. Network parameters are trained through variance of gradient descent. And the gradients are computed through backpropagation, which we have seen in the previous lecture. So the fundamental difference between classical feed-forward network and a convolutional neural network is that you have this extra convolution operation instead of a simple fully connected network in the initial layers, which takes advantage of the grid structure which is present in the input and helps us to reduce the number of parameters that have to be learned. Is that clear? Yes? So this is a convolutional neural network. One variant. The next variant I have for you is a recurrent neural network. Okay? So convolutional neural network, as I mentioned before, is for handling grid structures like images. Recurrent neural networks are used for modeling sequences. And a basic representation of a recurrent neural network is this, which is through a recurrence relation. Are you familiar with that? Yes, a recurrence relation. Okay. So these models that I have drawn here, they actually have these loops, and these loops implies the recurrence relation which exists in that network. What does that mean? I can actually unroll this network across time, over time, and I can show to you how this will look like. So we are at some hidden state. Let's say it is h minus 1. When you observe that sample at t equal to 0, which is x of 0, you're passing that as input to this block, and that block here refers to the hidden layers, right? The hidden layer takes as input the hidden layer representation from the previous time step and the input observed at the current time step. It looks at both of these quantities to predict what is the output. Now, when you go to time t equals 1, you have a fresh input which is arriving, which is x of 1. You have the hidden state from the previous time step, which is h of t equal to 0. So at t equal to 1, the hidden state, right, h t equals 1 is a function of x at t equals 1 and h at t equal to 0. Right? And this kind of proceeds as you go across time. So if I have to make a generic statement, ht is a function of xt and ht minus 1. And that's the recurrence relation that you have. Yes? And every time step you have a specific output. And the output here depends upon the hidden state which is outputted at every time step. So yt is a function of, let me clarify this. This is fh, this is fo of ht. Just to say that it is not the same function. Okay? And what are these functions? Again, simple linear aggregations with some nonlinear activations applied to it. Right? So I can expand this as a set of input weights. Let's call it wi transpose xt plus a set of weights connecting the hidden layers transpose ht minus 1 and a nonlinear activation which is applied on it. Yes? Clear? Yeah? Good. So this is a very, very basic recurrent neural network. I can have multi-layer recurrent neural networks where this recurrence relation spans across multiple layers. So in this case, I have one hidden layer. This is the first hidden layer where I have this recurrence relation. I have another hidden layer where too I have recurrence relation. I can also have skip connections, right? Where this contributes to this, right? So we can draw here. So the hidden layer at time step h1 at t, h2 at t, right? Currently we have that this is connected in this way. I can also have a connection like this. So this is ht plus 1 at the first layer. This is ht plus 1 at the second layer. So I will have this connection and so on. So you can design any kind of such recurrent neural network, encoding different kinds of dependencies from one time step to the next time step. Is that okay? Great. So the equations that determine a recurrent neural network is basically these two, right? So this is just a one layer recurrent neural network, right? So you have only one hidden layer. This is what I have written this particular equation. Okay, so this part is okay. Let me just skip this. If you have two layers, then this is the equation. I'm again going to skip this because I can see you're zoning out. So I'll give you some examples of variants of neural recurrent networks, and I want you to guess applications of those recurrent networks. Okay? Is this a recurrent network? No. It is a simple feed-forward network. It can be a feed-forward or a convolutional network. How about this? Is it a recurrent network? One-to-many. So what does this mean? You are giving one input, but you are expecting a sequence of outputs. And that is a recurrent network. You need to have a recurrent network, right? The simplest way to imagine is it is the same input which is fed at every time step. Right? What is an application for such a network? Where you have only one input, but you expect a sequence of outputs. Can you think of an application? Yeah, I want a concrete example. Think. So a very simple example, perhaps this is simple for me because I come from this domain and I work in this domain also, is an image captioning problem. The input is a single image, the output is a caption. And what is a caption? A sequence of words. Is that clear? So the input is just a single image, the output is a sequence of words. So that is a one-to-many. Can you think about the next one, many-to-one? The input is a sequence and the output is just a vector. It is not a sequence. That's the simplest thing to hit at, right? So the inverse operation. So given a caption, can we generate an image? Is there any other thing that you can, any other application? Another application is sentiment analysis, sentiment classification. You have a sequence of words, perhaps a tweet, which is basically a sequence of words. And you want to predict what is the sentiment expressed in that tweet. Is it a positive sentiment or a negative sentiment? You have a book review. You want to look at that book review, which is basically a sequence of words, and from there predict whether it is a positive or a negative review. So you have a sequence and the output is a vector or a matrix, whatever it is, but it's not a, definitely not a sequence. Can you give an example for many-to-many? The input is this sequence. After the input is seen, after the entire input sequence is seen, you start getting outputs. Next. Okay, auto completion. Okay, any other example? Search. The input should be a sequence, output should be a sequence. The standard example is weather prediction. Fine. So what you're saying is you're looking, the input is a sequence of weather conditions over a set of days. The output is the weather conditions over the next set of days. Fine. Future prediction. Fine. That's a good example from the domain you're coming from. Another simple example is machine translation. You have an English sentence and you want to translate it to Hindi. You want an English sentence or a Hindi sentence and translate it to, say, French. And the reason why I am saying that is you need to look at the entire sequence before you start making your predictions. Otherwise, you will end up with incorrect predictions. Right? You can't do one word at a time. You have to look at the entire sentence to get the full context, right? What could be many-to-many like this, where The moment you're seeing an input, you're getting an output. When you're seeing input, you're getting an output, but there is also a sequence structure to input and output. That is, you don't have to wait to see the entire input to start giving the outputs. That is a good example for that, right? Speech to text, right? Okay, good. So these are all examples of applications where sequence modeling is essential. And one way to go about doing is through recurrent neural networks. And the fundamental difference or the fundamental addition to a recurrent neural network is this recurrence relation. Okay, but that kind of complicates the entire training pipeline. The forward pass is straightforward. Remember that this set of weights which I told you, right? WHT, does it change from one time step to another time step? No, it remains the same. Okay, so the weights connecting one hidden layer representation at time step t to the hidden layer representation at time t+1, the weights there, they remain the same at every time step. If they keep changing, then there is no concept of a recurrent network. Okay, so they remain the same. So given an input sequence x0, etc., given the set of initial weights, you can always get what is the output. And once you have the output, you can compute the corresponding losses. And once you have the losses, you can compute the gradient and do back propagation. And that back propagation, when you have sequence, is referred to as back propagation through time. Okay, so for the forward pass the entire data sequence through the network and generate the outputs. And in the backward pass, you compute the gradients through back propagation. Now, something very interesting is happening. What is that? The loss that you get at every time step, okay, will it have an influence? Let's say the loss you compute at yt, at t equals capital T. Will it have an influence for the weights that you observe here? Yes, right? So let me make it much more clear. Let's look at time capital T and look at time capital T minus 1. Okay, so you compute the loss or the gradient of the loss at time t with respect to h t. Okay, now you have to compute the gradient of the overall loss with respect to h t minus 1. And what is this overall loss? It will have the loss at individual time steps which are summed up. So capital L is summation t equals 1 to capital T, L at every time step. Okay, so now if I have to compute dou L by dou ht minus 1, what are the two terms that I have to look at? H L capital T and L capital T minus 1. So you will have this particular loss, right? This particular gradient, right? And you would also have to look at, and how do you get this? Chain rule, right? So this will turn out to be yes. Now think what is happening if you go to H0. There will be, what will be there? So here I have, if I have to compute this, so I have this term, right? So now if I go to ht minus 2, I will have and so on. So what do you have? Yes, you have this product. Yes? Everyone is clear with this? Just coming out of the recurrence relation. Okay? Now, if these terms, if each of those gradients are less than 1, what happens to this product? Becomes very, very small, right? And the gradient, the overall gradient becomes very, very small. That is referred to as vanishing gradients problem. Because you need this product to actually update with respect to the first input that you're getting to the network, right? Because the gradient has become so small that the update there doesn't make sense there. On the other hand, if each of these values are slightly greater than 1, then what would happen? Yeah, it starts exploding, becomes a very large value. That will result in exploding gradients. Right? So if each of those values are slightly greater than 1, you are multiplying multiple terms which are greater than 1, eventually it will come up to a big number. And that will lead to a weight update which has some significant impact for your later iterations. Right? So in either of these cases, we actually have a problem. One is either vanishing, the other is exploding gradients. And those are some of the main drawbacks of your classical recurrent neural networks. Okay? So they are excellent models for time series prediction, time series classification, sequence prediction, and so on, but they suffer from vanishing and exploding gradients. And one solution to at least address this vanishing gradient is through a long short-term memory network. Okay? And the idea is the following. What is contributing to this vanishing gradients? This multiplicative term. Instead, if it is an additive term, then you won't have this problem. So a long short-term memory has this superhighway, right, which is connecting from one time step to another time step, but the interaction is additive, not in terms of multiplication. And that prevents, in a very, very high level, that prevents the vanishing gradient problems in long short-term memory, but it can still be exposed to exploding gradients. Okay, so with that, I will stop today's lectures on a quick introduction to machine learning, deep learning, in particular feed-forward networks, CNNs and RNNs. And I just thought I'll have one slide to talk about where ML and tipping points, in my understanding, can work. Okay. This is something perhaps that is relevant to what you are all working on. The first is classification of tipping. That is, if you have a temporal system, right? And if you're looking at the data prior to the occurrence of tipping, can you use it in some way to classify the type of tipping that might occur in future? So in my, very, very preliminary understanding, please bear with me if I'm using the wrong terms because I'm not an expert of this field, right? So if you have, if you can categorize it as catastrophic transition, that is a critical transition, or a non-catastrophic transition, or no transition, or smooth transition and no transition, right? So given a sequence prior to the occurrence of the tipping, can you predict what will be the type of transition which will occur in the future? You have already seen that, right? Vishwesha talked about it in the morning, where you were looking at early warning signals. And how did you capture these early warning signals? Well, you said, you observed empirically that autocorrelation has a strong influence, skewness has a strong influence, something a standard deviation or some other statistical measure has a strong influence. But those measures were designed by you based on your expertise, right? Now you can think about doing the same thing using a neural network, allowing it to learn whatever the features it thinks is important for the same task. But the challenge is, if you have to train a neural network, you would need large amounts of data. And from my limited understanding, real data is hard to come by in your field. So what can you do? You can take the approach in a couple of papers where they synthesize this data using the governing differential equations. The advantage with that is you can easily generate large amounts of data and incorporate some kind of features which allows for variability in this data, and at the same time a very easy annotation effort. You know the equation from which you are generating the data, so you can easily label it. Right? Fine. So far you are with me. So you have generated large amounts of data. Now you went ahead and you trained a deep neural network, probably used a convolutional neural network or used a long short-term memory or whatever it is to train the model. But what is the challenge? What is the guarantee that the test data that you're going to encounter in the real world actually follows one of those distributions? Not necessary, right? And that's what we have seen in one of our experiments. And I think Smita will talk about it next week, right? Right. So for example, if you were to train your models on one type of smooth transition, and during test time you encounter a sequence which exhibits a different kind of yet smooth transition, the model may fail. How do you ensure that such distribution mismatches are handled? That's an important problem. And there are some ready solutions available in the machine learning literature in terms of generalization, transfer learning, and so on. Right? Second, classification of typing in spatio-temporal type. And this is, again, one problem which we were looking at. And the challenge we faced here is even synthesizing the data was hard, extremely hard. Right? Previously, the temporal part synthesizing was easy, but we had issues with distribution mismatches. But for spatio-temporal systems, even synthesizing data for training a network was hard. So how can we, and not just synthesizing, but to synthesize in a way that you can capture the discriminative information across these different types of transitions, right? In a non-trivial fashion. That was quite hard. And again, even if you were to train it on synthesized data, there is no guarantee that it's going to work with real world data. And finally, forecasting the tipping itself. When will it occur? Which is basically a regression problem, right? Can we do that through machine learning? There are techniques to do regression. You can apply regression for neural networks. You can generate synthetic sequences and see if it is going to work or not. Again, this is an open problem. Even if you were to forecast it on your synthetic data, how many real world data sets do you have to actually validate whether your model is actually performing well or not? Again, a huge challenge. With that, I end my lectures on machine learning. I hope you at least picked up the jargon and you had a good idea, okay? Perhaps not in great depth, the mathematical part, but at least you had a good overview of how neural networks function and what are the important variants of a neural network. And the lab that Smita is going to do next will probably reinforce some of these concepts, and you have enough material now to pick up papers on these topics related to your domain and work on it. Okay, thank you.